This is like a bonus section. So I mentioned in the thumbnail that we will be doing the Fibonacci sequence. This is a very famous sequence, but the way you get the sequence is very interesting. So the sequence goes like this. You have 1, 1, 2, 3, 5, 8, 13, 21, and then so on and so forth. And the way you get the next term is, so the first two terms are just given. So you have 1 and 1 given. Okay? You have that given. The third term is the second term plus the first term. So third term is equal to the second, t for term, plus the first term. The fourth term now is actually given as the third term plus the second term. So now you can see with sequences you can get very creative. You can do whatever you want. You could multiply it, but in this case we're just adding them. So you can see 8 is actually 5 plus 3. That's how you get 8. 13 is actually 8 plus 5. 21 is actually 13 plus 8. So once you're given the number 1 and 1, you can continue. So let's make our own Fibonacci sequence, right? Let's call it Maths with Musa sequence, because why not? Let's call it that. And how would you do that? Well, let's say we start with the numbers 3 and 4. Now we can make our own sequence. So the next term is going to be 3 plus 4, which is 7. Then after that, you would have 7 plus 4, which is 11. Then you would have 11 plus 7, which is 18. Then you have 18 plus 11, which is 29, and so on and so forth. Now, what's the interesting thing about this? You might be like, this is just a random sequence. We just made stuff up. Now, the interesting thing is, if you take the next term, so we have the nth term, and then we have the n plus 1 term, right? If you take the next term divided by the term before it. So let's say we did 4 divided by 3 in this case, right? We have 4 divided by 3. That's approximately 1.333, right? Recurring. Let's say we did 7 divided by 4. Well, that's approximately 1.75. That is 1.75 actually. That's equal to 1.75. Let's say we did 11 divided by 7. Well, you end up getting 1 point something, 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 right? You'd end up getting some decimal. In this case, 1 divided by 1 is 1, 2 divided by 1 is 2, 3 divided by 2 is 1.5, 5 divided by 3 is like 1.667, 8 divided by 5 is 1.6, 13 divided by 8 is 1 point something, 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 something. Now the interesting thing is, and this is why it's so famous, is because all these numbers, like look, here we made our own first two numbers up and then we continued the sequence. But these numbers here, as you get like bigger and bigger numbers and you can try yourself, they approach a value, and this has a special name. So we denote it by the Greek letter phi, and this is equal to 1.618, so on and so forth. Of course, this is also like never-ending decimal. This is like up there with the level of pi and other numbers as being very useful, because this is actually called the golden ratio. And the funny thing is, or the interesting thing is, that it appears in so many things. It appears in like sunflower, it's like the way the sunflower petals are, the sunflower seeds are. It's like a lot of stuff in nature is very related to the golden ratio. Stuff in your body is related to the golden ratio. So like if you measure so let's try this experiment if you want. So measure the distance from your hip to your toe, or hip to the floor, and then measure the distance from the knee to the toe. And you will see that once you, so let's say you get this number as like number x, and you get this number as a number y, right? When you do x divided by y, it will actually be equal to 1 point something, something, something. And science has shown that the closer this number is to 1.618, which is the golden ratio, that's, I guess, the more scientifically perfect your body is. That's like the ratio that humans find, appealing or attractive. And something on your face as well, like the distance between your eyes to your nose, and literally everywhere, even in Da Vinci's drawings. If you've seen the famous drawing, the Vitruvius Man, right? It's like a man, and he's like, I'm very bad at drawing, so I'm not even going to try to draw it. But it's a famous drawing by Da Vinci. I'll try to put it up on the side. You will see in that drawing, he uses the golden ratio as well to like get the measurements correct, because this actually occurs a lot in nature and in our bodies and everything. You can try these experiments. You can try actually from shoulder to fingertip, shoulder to finger. And you can also try from I think it's your elbow, from your elbow to your finger. And of course, no one's going to be exactly 1.618. And if you get 1.618, it doesn't mean you're perfect. But that is what like the ideal body measurements are. So you might end up getting like 1.4, for example. Here you might end up getting 1.7, and here you might end up getting like 1. Oh, sorry. If you did this ratio divided by this ratio, you might end up getting something like 1.4. While at this ratio to this ratio, you might end up getting something like 1.7. Doesn't mean your body's not perfect. That just means that it just shows that 1.618 is there somewhere, and like you don't have to believe it, but it approaches 1.618, especially in this sequence right here. Once you get higher and higher up, you can find proofs online that's like very complicated, not for our level, but they do approach 1.618, and that's why it's called the golden ratio, because it's so common and it's so unique, like the way it came about. It came about when like this famous mathematician, his name was Leonardo Fibonacci. He was studying like how rabbits populate the environment. So like if you put one rabbit and then you put another rabbit, so that's 1 and 1, well, you get 2 rabbits, and then they will reproduce to give you 3 rabbits, and then these 3 will reproduce to give you 5 rabbits, and then those 5 will reproduce to give you 8 rabbits, and then so on and so forth. And well, that's the Fibonacci sequence. That's how it came about. And now you can see it has so many different applications in nature. So yeah, hope that's interesting to you.